Okay, problem 4a, my favorite thing to do with infinite series is to write a repeating decimal as an infinite series. So super cool that you can do this, I think. So the key to recognize here is that, remember, we're dealing with an infinite series, so we're going to continue to be like adding all these different things together forever. And we need to figure out a way to represent this by adding things together. And it's hard at first because you might want to set up a series where you're actually going to end up adding too much in, even though it seems like it might be right. So this is the thing to recognize. If you let your first term be everything that is repeated, that is like the pattern that is being repeated. So for example, let your first term be that decimal 0.42. So we're going to have a sub 1 is 0.42. Well, we're going to need to add that to a sub 2. And we don't want to add something that's going to have a 0.42 right there, because then we're going to add those 0.42s and we're going to get 0.84, and that's clearly way bigger than what we want. So we need those two spots to be zeros, but then we need our 42 after that. Similarly, with our third term, we need 0, 0, 0, 0, 4, 2, and our fourth term to be 0.000000, 4, 2. Because when you add all those together, when you compress them, put them all together, you're going to get that 0.42, 4, 2, 4, 2, 4, 2. And you can see how if we continue this pattern, it's going to keep going. So, like any geometric series, we need to figure out all we need to do to write this is figure out our constant term, and then, our constant term, I can't talk, our first term, and then our constant ratio. So set it up like normal. We'll go from 1 to infinity. Well, our first term is 0.42, and I'm going to write that as a fraction, which is 42 over 100. That is our first term. Now we need to multiply that by our common ratio, and we need to raise that ratio to the power of n minus 1. So this is where it gets a little tricky. So notice that, let's do this. Let me erase some of this stuff. So notice, I'm going to go equals. Notice that 0.42 is just 0.42. I'm really bad. That's boring. Let's look at A2. 0.0042. Well, that is 0.42, or to keep it as our fraction, that's 42 over 100. No, let's do it as a decimal. That is actually easier. So that's 0.42, but we need to move that decimal place. 1, 2, and wow, Mr. Reed, you can't do math today. That's 0.42, but we need to move our decimal place 1, 2 spots to get the 0042. Well, to move a decimal place 2 places to the left, that's like, well, if you take 0.42, ignore those equals. If you take 0.42 and divide it by 10, you get 0.042. If you divide 0.042 by 10, you get 0.0042. That's what we wanted. So we had to divide by 10 twice, which is like saying we had to divide by 100. So our common ratio is going to be 1 over 100, because then each time we will divide by 100. Each exponent is going to increase that and move it 2 decimal places. So I'll continue to get my repeating pattern. Isn't that cool? I think it is. So there's that, and now we want to know what's the sum, so we use our formula. Since our ratio is most certainly less than 1 and greater than -1, we can use our formula that says take your first term, divide it by 1 minus your common ratio. So we do that, and we get 42 over 100 equals 99 over 100. Notice 100 and 100. Those are going to cancel out, and we're going to be left with 42 over 99. That's so cool, and that's how you write any repeating fraction. You just take the repeating part and divide it by that same number of 9s. So since there were 2 decimal places in the repeating part, the 4 and the 2, we had 2 9s, the 99. That's awesome, and that will always work. That's so cool.